We're going to continue to look at vectors today. We're going to start off with dot products. In some of the things that are done in with vectors, this idea of what we have over here where you multiply the two x's together and then add what you get when you multiply the two y's together showed up so much they just gave it a special operation called a dot product. So the dot product of u and v is basically, once again, as I said before, multiplying the two x's and add it to the product of the two y's. So you're going to be ending up with a number. So in other words, dot product is a scalar, not another vector. So here we have three vectors, u, v, and w. We're going to start off by just doing a dot product of u and v. To do the dot product of u and v, once again, you got to multiply the two x's and add what you get when you multiply the two y's. And so then you get 28. Over here, we got to follow order of operation, so you got to add u and v together first. So here's u, or not u and v, v and w. You got to add your x's, add your y's, and so then you end up getting negative 4, 6. And you want to do a dot product with u, which is a 2, 6. So once again, multiply your two x's, get negative 8, add your two y's, get 36, and once again you get 28. Will you always get 28? No, it just happened to work out that way with these two examples. So don't assume that it will always happen, because it won't. Now, you can also find the angle between two vectors. To find the angle between two vectors, where your angle is theta, you want to use this green formula. Cosine of your angle is your dot product, and then it's over the product of the two magnitudes, the length of A times the length of B. Now, two vectors are considered parallel if the angle between the two vectors is 0, which they'd be parallel in the same direction, or pi, which would be parallel and then in opposite directions. Now, two vectors are orthogonal, meaning they form a right angle if the angle between the two vectors is pi over 2. Well, you should remember, orthogonal forming a right angle is pi over 2 or 3 pi over 2. But for either case, the cosine of pi over 2 or 3 pi over 2 is 0. So if you have two vectors that are orthogonal, the cosine of that pi over 2 is 0, so the whole left side becomes 0. On the right side you have a fraction. What's the only time a fraction is ever equal to 0? And that's when the top is equal to 0. So in other words, when the dot product is 0, you automatically know the angles are, or vectors are, orthogonal. Well, let's go ahead and find the angle between these two vectors. So we've got to go ahead and use that formula. So we need to go ahead then and do the dot product. Once again, multiply your two x's, add what you get when you multiply your two y's. Then we've got to put it over the magnitude. So you got to do negative 2 squared, which is 4, plus 3 squared, which is 9. Add it together, it's the square root of 13. Then you got to do the same thing for the next one. And so you go 1 squared plus 5 squared, or 1 plus 25, or 26 inside your square root. Well, it does simplify a little bit, but it's really not going to do a whole lot. If you just wanted to go ahead and do the cosine inverse to find your angle of the first one, you could. If you did simplify it, you get this here. When you type this in, you want to make sure you have the whole denominator in parentheses, otherwise you'll get the wrong answer. So you type this in, and then assuming that you're in degrees, then you get an angle between the two vectors to be 157.62. Are these two vectors orthogonal? Well, remember, for vectors to be orthogonal, the dot product has to be 0. And so when these are orthogonal, because when you do your dot product, multiplying your x's, you get negative 4, multiplying your y's, you get 4, and that adds together to give you 0. So yes, they are orthogonal because our dot product is 0. So now we want to find the angle between two vectors is theta, and the vectors of a and b here. Well, we now want to find the component of a along b, and that's denoted as this here. Basically, you're taking the angle between two vectors formula and then just multiplying both sides by the absolute value or magnitude of a, and that's your component of A along B. Don't be real concerned about that for the sake of your homework and your tests, but we will touch on that here. Now we'll go ahead and we'll look at work. Remember, work is force, which we're calling vector A, as it's done in a particular direction, which is D. So work is force times distance, or the dot product of the two vectors. Here we have a piano again. Once again, it's a 500-pound piano. And it's on an incline of 45 degrees. Well, for the most part of the weight of the piano is perpendicular to the ramp, or the weight of the piano on the ramp. The rest of the weight of the piano is really parallel to the ramp, meaning the amount of force it takes to keep the piano from going down the ramp. So here we're looking for that force required to keep the piano from rolling down the ramp, and that's the parallel to your ramp. So we're really looking for this side over here. Well, if we're looking for this side here and we have a right triangle, all we have to do then is use our sine. So the sine of 45 is equal to opposite over hypotenuse. Multiply both sides by your 500. And you get 500 root 2, because you should remember the sine of 45 is 2 root 2. No, not 2 root 2. The square root of 2 over 2. Or the approximation then is 353.6 pounds to keep your feet, or the piano, from rolling down the ramp. Well, here we have another problem. We're dealing with a man pushing a broom at a constant force of 40 pounds. And the broom makes an angle to the floor of 30. We want to know how much work is done to push it 30 feet. Well, there's really two ways to do this. Now, the first way is to look at your force in the direction of your movement. Well, our force in the direction of the movement is really this blue part right here, because you're pushing the broom horizontally 30 feet. So your force vector here can be broken up into its components, the vertical component and the horizontal component. It's the horizontal component that we're interested in because your broom is moving horizontal. It's a right triangle, it's adjacent in your hypotenuse, so you use your cosine, you solve it for cosine, and you get 20 root 3. Once again, your distance is 30 feet. So your work, once again, is force in the direction of your distance. So here's our force, here's our distance. We multiply them together. 600 root 3, really foot-pounds here, that's a little typo, or approximately 1,039.23 foot-pounds. Well, the other option is to go ahead and do the dot products that we talked about before. Now, your force vector here has to be broken into its component form before you can do the dot product. We just figured out this horizontal piece right here of 20 root 3. So your horizontal part is 20 root 3. Well, how do you figure out the vertical part here? Well, that's not too bad to do because it's a right triangle once again. So then you could do your sine of 30 degrees is equal to your opposite, the y, over your hypotenuse of 40. Now, remember that your sine of 30 is 1/2. And so then you get y to be 20. However, keep in mind your vector is going down, and so that's why we have a negative 20. Well, then your distance is just going horizontal 30 feet, going down 0, so you do your dot product, multiply your x's, and add what you get when you multiply your y's, and by George, you get the exact same answer.